So let's recall where we are. And let me again just start with an example. Remember that if, say, x is a wedge of 3 two-spheres, I can look at points inside those. I might switch back to AWW app if this is sort of not as smooth for me, but we'll see. I've got points in each of those, and yes, I want to consider a map from a sphere, say a 4-sphere into X. And the approach was to look at pre-images and think about those is how we're thinking about pullback in cohomology. So I let P be the pre-image of little p, and etc. And then I let Q and R be the same. And then what I'm going to do is choose these D inverse. Again, it's a choice of some cochain which co-bounds, in this case maybe tau capital P, to be itself a tome cochain, but I'll just call it D inverse of P, where this is something so that the boundary of D inverse of P is P. So that's just another submanifold of one higher dimension, but that means one lower codimension, which is then co-bounding. So we'll do it that way. And I'm also going to omit all taus. So that's just going to save us a little space in drawing. And so what I said is we want to consider the bar construction on the cochains of X. Let me zoom out just a little bit. And then, for example, little p bar little q bar little r will be a cocycle because p, q, and r are sort of submanifolds. Now, of course, X has a wedge point, but for these purposes, we can really think of these as submanifolds. So the co-boundaries will be 0 because these submanifolds have no boundary. And these are also disjoint, so the cut product, at least at the cohomology level, is 0, and it would be, if you're using Durand theory, say, it would be 0 on the nose. So that's this cocycle, gamma, and we pull it back, and we have capital P bar capital Q bar capital R. And what we then need to do is, actually, let me move this over a bit, sorry. Give myself a little more space. So we have capital P bar capital Q bar capital R. And in this bar construction, this is now in the cochains of the 4-sphere in this case. In this bar construction, I can, again, it's the same game by taking D inverse, but if I take D inverse of just one of these, again, D inverse means a choice of co-bounding cochain, then under the Leibniz rule, when I take D of the first term, I get exactly this. And the D of the other two terms will be 0 because Q and R are closed. So that's the Leibniz co-boundary. But then there's the other co-boundary in the bar construction where I would have D inverse P times Q bar R. And this time could be cup if we're dealing with integral cochains, or wedge if we're doing Durand theory. And then you have to move the axes down a little bit. Then you have to play this game again. And there's a couple choices. You could either co-bound D inverse P wedge Q, and let me realize that, and let me pause for just one moment. Let me make sure I can see the chat. There we go. So far, nobody's posted to the chat. That's probably the best way to get my attention. In any case, let me move that over here. So I can co-bound by either co-bounding on the left again. So that would mean a D inverse of this D inverse P times Q bar R. That exists because, once again, this is what P was like a 2 cochain. D inverse P is a 1 cochain. Q is a 2 cochain. The cup product would be a 3 cochain. It's closed by the Leibniz rule. So therefore, it must co-bound. You know, or I could have also picked on the other side. I can take D inverse P times Q bar D inverse R. So not only is there choice in these co-bounding cochains, and again, I'm thinking of those as co-bounding submanifolds of 1 greater dimension or 1 less codimension, but there's a choice on sort of which way I reduce. Either way now, if I take the other boundary, in this case, I would get the cochain D inverse of D inverse P times Q times R. And in this case, I would have D inverse P times Q times D inverse R. And this is what we'll call our Hopf cochain. These are 2 different choices for Hopf cochain for this cocycle. And you know, geometrically, the second one is sort of easier. This is the picture that I drew last time of 2 surfaces, P and R, being co-bounded and intersecting with Q. That's a higher linking. This is also higher linking, but it's more sort of iterative. I co-bound, intersect, and then co-bound that, and then intersect. So these, as we started with last time, are invariants. But let me now actually, with this example in front of us, makes some definitions and theorems. So the main definition, so if I have, excuse me while I move this up. If I have a cocycle in the bar complex on the cochains of a space, then I can define let's define it to be, so sorry, there's going to be a bit of conflict of notation for my paper. Let's just define H of the pullback of this cocycle to be any choice of weight 1, or you could even say weight 0, cocycle cohomologous to gamma. Okay, and then define our Hopf invariant. I'll just call it eta of gamma. And this is going to be a way to take a homotopy class of map to X. And the way it will be defined is that we're going to take that its value on F is going to be, well, pull back gamma, take that tau, any choice, and evaluate it on the fundamental class. So pretty slick definition in the end, and we've seen from examples that this is capturing some geometry of linking, because when you find this tau, you find yourself co-bounding things, taking products, and that's exactly what linking is about. So let me go through the things that we all in this audience will know you'll want to do when you make such a definition. So the first question, and let me move this again. Is this well-defined? Well, I won't go into details, but yes, and that's pretty easy. And this is both up to choices of D inverse and how you reduce, and and up to homotopy. So I'll just say relatively, but we won't talk too much about that. Q1, the next question. Do these give us everything we want? Do these span the homomorphisms from the homotopy of X into Z? Let's again assume for Q0 that's fine as it is, but now let's assume that X is simply connected. And the answer is, well, not quite, but yes, up to finite index. So note, let me say a little bit more about that. So note that for X an odd sphere, with a cohomology of X in the top degree is spanned by, say, some iota, then then gamma equals iota bar iota gives the classical Hopf invariant. And so now some folks know. So well, let me do it this way. So define with that. So let's define the Hopf invariant quotient of X to be all the ways that we can measure homotopy, just abstractly, modulo these the image of this bar construction on the cochains of X under these Hopf invariants. And then Adams says that the Hopf invariant quotient of X is, well, it's 0 for, sorry, not X in general. He was just concerned with spheres. 0 for n even. There were no invariants to begin with. There were no non-trivial. There's only torsion in those degrees that one could ask this question. And it was also 0 for n equals 3, 7. You could also say 1, but it's z mod 2 for other odd degrees. And that's, of course, a very deep fact. And let me move the whiteboard. So now we have a fun little homotopy theory question that we can amuse ourselves no matter how long we have to spend indoors. We can just compute Hopf invariant quotients all day. So, so the other thing to note is that, of course, if we switch from homomorphisms into Z to homomorphisms into Q, we actually then would have an answer of yes. These invariants span all those homomorphisms. And we'll talk about that later. That's going to be the main result we'll talk about today. But I wanted to get to the next question, which is, are there relations among these? Really, how many are there? So for example, if I use a commutative model for cochains, in which case I would have to look at really real valued homomorphisms, or for those who know, the commutative model for cochains on a simplicial set, in which case I'm looking at rational valued, but the definitions go through the same. Then for any closed alpha and beta, you have that, or actually, let me just do A and B, because you have A bar B minus plus B bar A is a cocycle. That's because we're using commutative cochains, but the resulting Hopf invariant will be 0. So this is there definitely are some relations. And to discuss the relations, I want to go back to some geometry then. So the geometry is a different way to interpret these expressions. So let me just say there's some more geometry, not just geometry of linking. We're going to see our friends, or at least my friends, configuration spaces. I know it's an odd friendship, but they are dear friends to me. So let me give you a claim. So let's think about a slightly more general example than before. Suppose I have a D sphere mapping to a wedge of spheres, and then we have our points in here, and then our capital PIs are their pre-images. Then the claim that I want to, the claim that I want to prove next is that these Hopf invariants encode the following data. So if I then look at the product of these spheres, and yes, the PI are in the D sphere, but I'm going to really think of them inside of RD because they're disjoint from the base point. So if I take the product of those, and so then I'll just look at x1, however many there are, xk in here, then those points can just, well, I can remember that there's inside RD and get a configuration. There's a bit of a lag, but there's what I was just writing. So this is kind of a funny thing. Let me, it's funny, but it's then immediate, and it goes back to at least Gauss, probably exactly Gauss. So an example is if F maps for S3 to S2 wedge S2, Then I've got P1 and P2 look like this. So this is my capital P2. This is my capital P1. And then the product of P1 and P2 would be a union of two tori. And for every point in the product, I can just, that's abstractly, it's a union of two tori. For every point in the torus, then I've got a configuration of 2 points in R3, because I can just remember what those 2 points are. So x1, x2, we're on the P's and Q's. Similarly, if I have some, in my first example above, I have P cross Q cross R. These are all inside R4, and if I take a point on each, that gives me a configuration of 3 points in R4. Yep, I will move up. Thank you, Adam. I'll pause a second to let people digest. So all we're doing is we're taking these pre-image submanifolds. Now, again, this is a special case. The bar construction and the theorem that I said works with all this linking with correction, and you have all sorts of complicated cocycles. But the first ones to really make peace with are these ones where I've just got disjoint cocycles in X, and then I look at their pre-images and they're disjoint submanifolds of the sphere, and then I'm taking linking and I'm saying, here's an alternate approach to linking. The first approach was co-bound and intersect. And then the second approach was to, well, is what I'll say now, is to think about configuration spaces. So let's look at this claim that Hopf Invariants encode, and let's start discussing why these two approaches are the same. So hopefully folks were able to either attend or download the catch-up lecture, because we'll now use some facts about configurations. So let's remember, so if I've got configurations of endpoints in RD, I'm just going to define top to be the number n minus 1 times d minus 1. And then the top dimensional homology, oops, the homology and top degree of configurations of endpoints in RD is something that that we can call, that's often called Lie n. And let me just jog your memory a bit. This is spanned by, say, upper half planar trees. And then depending on whether n is even or odd, I'll do the version, I think, where I want n to be odd. N minus 1 will be even. Then we get the classic anti-symmetry relations and the classic Jacobi identity. Let's remember that, or, you know, so if you missed it, this thing is associated to a submanifold where I've got orbital systems. I've got point 2 orbiting opposite system where point 1 orbits opposite points 3 and 4. So these are some definite homology classes, and one can, and then they span, especially once you allow forests, disconnected trees, they span all of the homology. The top dimensional homology will be just connected trees. Every single label is going to appear somewhere. So there's no labels off to the side. And again, thanks for sharing. By the way, if you're on the YouTube, there's up and to the left, I will sort of put an arrow here for now. There's this, the ID of the whiteboard. If you type in whiteboardfox.com / that series of numbers, you can see the whiteboard, and that way you're free to scale it and move it. Again, thankfully, you're also not free to add to it, which I know just people do it by accident, but that's why I'm going to try this whiteboard this time. So, so moving it back, then what's less familiar is that the top cohomology has a lovely presentation, which is not just a formal linear dual. And to call attention to that, I have some fun with the name. I call it Isle, which is Lie backwards, although you could also say it has something to do with Eilenberg too. It's, and these are spanned by graphs. And they have to do with, as we'll say in a moment, in fact, if you, to really talk about them at the cochain level, I would label them by vectors. And they have to do with a submanifold, that they're represented by the tome cochain of the submanifold, where the vector between x1 and x2 is the that unit vector in that direction is v1, and the unit vector in the direction from 1 to 3 is v2, and the unit vector in the direction from 3 to 4 is v3. And there's also some relations here. You also have an anti-symmetry, but then the dual of Jacobi is Arnold. It's a dual that waited a couple hundred years to occur. And this is a presentation for the top dimensional cohomology. And then one of my favorite objects, something that, well, Reutenauer sort of found it originally, and then Paolo Salvatore and Victor Turchin and I found it independently for the same reason, working on knot spaces. You can then take every edge here and think about the path that goes in the tree there. And if you do this all over all edges, you can look at the bottom of each one. And then you ask, are these points that are the minima on these paths, or the greatest lower bound between the two leaves? So if I have leaf 1 and leaf 2, I can look at the vertex that's the highest vertex that's below both of them. If those are all distinct, then I've got the pairing between these two is going to be plus or minus 1, and that's the pairing in homology and cohomology. So let me just say, I like to put my cohomology on the left, my covectors on the left, and my vectors on the right, is what we call the configuration pairing. And of course, it's perfect by the universal coefficient theorem, which would be a way to then prove this combinatorial fact that is actually a lot of fun to just prove directly. So let me make a general remark as well. Just all of the homology I'm losing. Sorry, let me. I lost a little connectivity. Hopefully I will, okay, I'm back. All of the homology of the configurations of endpoints in RD, that has an algebraic name. It's part of the Poisson operad with degrees shifted by d-1. So how are we going to use this here? Again, I talked about the sum in the catch-up lecture, and then I'll happy to talk with folks about it in other venues if they wanted. So recall that there's a way you can make a free Lie algebra. So if V is a vector space or a free module, then LV is the free Lie algebra on V is isomorphic to the direct sum of these Liens tensor V to the n, because you can just V1 bracket V2, V3 bracket that, V4, V5. That's an expression in the free Lie algebra, and I can think of it as a tree 3, 1, 2 with 4, 5 tensor, and then I can just list the okay. So that's the operatic way to discuss free Lie algebras. Operads are exactly created to make such constructions, to keep track of the ways that you can multiply 5 things. I would, here's my 5 things that I want to multiply, and here's the extra data that I need to multiply them. So that's what operads provide, is some extra data. What information do I need to multiply 5 things? In a commutative algebra, you don't need anything more, and that's why the commutative operad is so simple, that it's the ground field essentially. But for other algebras, you do need more data. But then this point of view, so let W be a vector space and call EW the direct sum of this Isle module. So by abuse, let me put this in red writing, because these are graded tensor products, but it's still, what I prefer is you've got the graphs, and now you're labeling them with W. Really what you need is, you'd want the analog of this, where you just have the underlying graph and then the list of W's. And then the claim is that, well, it's pretty immediate. Basic algebra is that if there's a pairing with, which is perfect on VW, for example, if I'm just thinking about W, the linear dual of V, then this extends to, under finiteness, to LV and EW. And so what we have every right to do at this point is call this, again with some finiteness, the co-free Lie coalgebra on W. Let's see, so I've got the tensor product, yes, is over the symmetric group. Thank you very much, Florian. Let me write those in. Thank you very much. Okay. So, so this is the co-Freely coalgebra, and what I should just say is, what is the co-bracket? Which I like to, people like to denote this way. Well, let me just give you an example. So the co-bracket on, if I, again, by abuse, just think of this as a graph now with elements of W. I take every edge. So these are acyclic. So note, these are acyclic because 0 if a cycle that follows by the Arnold identity. So we may assume this graph is acyclic, and that means that for every edge, if I just take this first edge from say W1 to W2 here, for every edge I can then remove it, and I get 2 acyclic graphs. And what I'm going to do is take those 2 acyclic graphs and tensor them together, and then I'll also add or subtract the reverse, and there's signs everywhere, which there would actually be no hope of working out the signs unless I use the longer notation with the tensor product around. And then you continue. I pick on another edge, say that the other one that I indicated there, and I would have W1, W2, W4, W3, tensor W5, and then tensor that same graph. And you go through all the edges, remove them once, one by one, and it splits into 2 pieces, and that's your co-bracket. So, so now let me just say that what we were saying before, so this is the co-Freely coalgebra just on the vector space, but we're going to have some other structures around too, some algebra structures. So now define the Lie coalgebraic bar construction of a commutative algebra with a differential graded commutative algebra to be this co-Freely coalgebra. So the original bar construction I told you about very concretely last time in this way would be the, you could call it the co-associative bar construction. Now we're on to co-Lie. And then I've got a differential that's going to be sort of come in 2 pieces. So first I'm going to have the differential on C extended by the Leibniz rule. And then I'm going to have some differential that comes from the multiplication on C. And let me just give you that by example. So what is the D on, I'll make a very small example, A bar, B bar, C is equal to, well, I can take dA to B to C, and then A to dB to C, and then also A to B to DC. That's all the Leibniz rule. That's what was sort of above. Let me use colors. So the Leibniz differential is all of this. And then I would have the contraction differential, which would be AB to C and AC to B. Oops.
It looks like you haven't set up any HomeKit accessories.
Sorry about that. And that's the green bit of the differential. So the differential comes in two pieces like that. And it's, so in particular, the co-associative bar construction maps to the co-Lie bar construction by sending A1 bar A2 bar AK to A1 arrow A2 arrow AK. So contracting an edge would correspond to removing a bar, and we're still multiplying in both cases. And then the, but there's, I should say, but this has, this is surjective, but this has plenty of kernel. In particular, because, you know, A1, A2, A1 bar A2, or A2 bar A1, both go to the same place. Let me move the board again. But remarkably, this is this co-Lie construction is exactly the right one for our purposes, but it did appear before. So let me first tell you in algebra this this definition for the co-Lie algebraic bar construction gives you a concrete way to write down Harrison, or you can think of it as a special case of André Quillen homology. So the Harrison or André Quillen complex. So that's really computing the cohomology of, homology of this is the natural homology for commutative algebras, in the same sense that Hochschild homology is a natural homology for associative algebras. So I like to remember Harrison's role here. He first realized that there were relations, there were cycles in Hochschild homology that were present if you were working in a commutative setting. And he figured out what they were there in terms of shuffles, and he presented this complex as a quotient of the co-associative bar complex. This is a sort of a different one, but in any case, it's actually isomorphic, just algebraically, to Harrison's. Harrison, by the way, was also faculty at the University of Oregon, so I enjoy the local flavor of the mathematics from my point of view. So the other proposition is that you know, gamma goes to take the Hopf form and evaluate, also defines a map from the homology of the bar complex on this Lie coalgebraic bar complex on the cochains with their, here I want some sort of commutative, so I should really say APL or something like that, but you could use standard theorem to the homomorphisms from the homotopy of X into Q. And then the main theorem that Ben Walter and I prove is that this is an isomorphism of Lie coalgebras. When you're looking at homotopy functionals, well, homotopy groups form a Lie algebra under Whitehead product, or really, I prefer Samuelson product, so that the signs come out better. And so the linear dual should be a Lie coalgebra, and this is a natural presentation for it. So, so there's all sorts of, and let me just say, and fits well with Quillen functors. Sullivan models even, etc. I realized as I was preparing the lecture today that I promised more than I would manage in an hour, but that's okay. Folks, I guess if you're watching, oh, this is not coming through on real time anymore. Let me do this. Sorry. Yeah, so there's a C star X is your favorite model of cochains that must be commutative if we want the Lie coalgebraic version. Again, if you're okay with, you can use integral cochains and cup product, that's fine, but sorry. But if you want the sort of the sharp versions of the theorem where you've got an isomorphism, then what you want to do is use something like the CDGA of rational forms on X. So that's why I say there, as I stated, that you could use APLX. I'm having some whiteboard trouble now, which is too bad. Let me see if I can get this whiteboard. The last thing I wrote, okay, and it fits well with, I think I'm back now, with Quillen functors, minimal models, etc. Okay, so we'll talk more about that next time. Let me give you the ideas of proof, because it's actually fairly elementary. You might say that, oh, okay, this is this this makes geometric Quillen's original isomorphism of, I'll be vague, a functor on the chains on X, the homology of a functor on the chains on X with the rational homotopy. So in other words, what Quillen was doing, one could understand from the point of view of linking. So, so again, if you don't think about homotopy is, but you think about how to measure homotopy, then we've got this geometry of linking. But let me now say some things about the let me just give some ideas of proof. The main idea is it's a simple induction up the Postnikov tower. That's a classic gem in algebraic topology. I mean, it's definitely something to really appreciate about the rational localization of homotopy, that the Postnikov tower isn't destroyed. Depending on what other kind of localization you do, Eilenberg-MacLane spaces can vanish, and the Postnikov tower just isn't there. You don't have any Postnikov tower. So the base case is for Eilenberg-MacLane spaces. Then, of course, you know, so we're looking at maps from X into K, Q, N, or not X. I just need an n-sphere. And of course, those are given by these Hopf invariants. The Hopf invariant there is already at weight 1. So you're just the first or 0th Hopf invariant is basically pull back cohomology and evaluate. Everything else is derived from that. So these are really derivations of, you know, the Hurevich image, and I'll probably say more about that next time. So, so the base case is extremely simple. It's exactly what you would expect for Eilenberg-MacLane spaces. And then you have to induct over fibrations. So you have the rational, the long exact sequence in rational homotopy for a fibration. And the nice thing is that the analysis of this of such for this Lie coalgebraic bar construction on cochains, again, maybe you want to think about. This ends up being entirely explicit. And as far as Ben and I could tell, and it builds on a sort of a twisted tensor product model for fibration. So you think about the sort of, really it's at the level of analysis that you can do for deducing the existence of the Laurent spectral sequence. So it's a sort of a basic thing, and we use the graphs here. Use graphs, not bars. We couldn't work it out for formulae. So this is the payoff for getting the right formulation. Is actually a pretty low technology proof that that you need. You just need, again, I'll just put it in red. You just need the Postnikov tower, and you need this twisted tensor model for a fibration. Those are both pretty elementary aspects of rational homotopy, and we get the isomorphism of the homology of this Quillen functor with homotopy groups. So, so yeah, despite my promise in email, my apologies, but I'll I think learn what pacing is better as I go on. I'll just now promise for next time we'll talk more about sorry. next time we'll talk more about tying together this approach with the with what Quillen did, which it's closest to what Sullivan did, and what Chen did for that matter. And then and there's more geometry. I mean, it's just a funny thing. Math to me is, well, I'm a topologist, so you know, when you have a hammer, everything in the world is a nail. I think of math as a space somehow, a simplicial complex. For example, you could have two theorems which together implied a third, and you could think of a simplex there. I'm just very naive. I'm not a homotopy type theorist or anything like that. But this is a subject that there's lots of really fun connections between the geometry and the algebra and the homotopy theory and things. And so unfortunately, time is, well, fortunate or not, time is linear. And so you have to sort of choose a path to navigate. So I've given you one development for that gets sort of the fundamental theorem of Hopf invariants in the rational setting, if as it is. But there's a lot more to say, a lot of things that other paths that we could have taken to put things together. And then I will also, I promise that I'll at least start, and let me just and start talking pi1, which is fun because this geometry, yeah, has it's manifest in purely algebraic pi1 lower central series kinds of ways. So next week I'll make all of these connections up here and start on pi1, and the following week I'll deal with pi1 and hopefully have a preprint to share that's very close. So I am going to stop sharing my screen. I'll take a couple questions, then I can stop the stream, and I will take more questions if people don't want any questions, their questions recorded on YouTube. So, sorry, let me pull up the chat. Right, so this will give a geometric interpretation of Milnor-Moore, absolutely, and that's something, yeah, and this is a very, so for those who don't know, I think the theorem that Manuel is saying, because there are different Milnor theorems, but there's going to be, let me maybe say a different thing, actually, because the rational homotopy groups of wedges of spheres, this will tell you how to measure them through these Hopf invariants. And yes, it would give you that calculation among others, because the Lie coalgebraic bar construction is going to be just the co-free Lie coalgebra. So I'll try to say that next time. I also realized that I didn't even explain why the Hopf invariants are, in the case of wedges of spheres, have to do with cohomology configuration spaces. So I should explain that too. I skipped to an aside, and I think I didn't say all that I wanted to. Any other questions, or you can wait for me to write. So yeah, so this will again be an important topic next time, the Chen approach. The bar construction on the cochains of X are a model for the cochains on loops. And then what you can do is, if you're thinking about the Hurewicz image there, so let's switch to homology for a second. Then you've got a cobar on the chains. And if you're thinking on the loops, you've got a Hopf algebra there. You've got a bialgebra and even a Hopf algebra in some weaker sense. And so you can look at the primitives, and that captures the Hurewicz image. And that's really been the starting point of Quillen theory, because the primitives on a tensor algebra end up being, or primitives in a Hopf algebra have a Lie structure. So yeah, hopefully I'll be able to address more of the interrelations between these different approaches, but this is a very important one. Now, so then the very quick answer to your question is that you can, let me go back to projecting my screen, sorry. And let me move things appropriately. So, and I'll say this next time, but since you asked that nice question, let me say it now. So you have homotopy of X is isomorphic to homotopy of loops X, and then you can map to the homology of loops X. And once I tensor with Q, this is injective. And so then cohomology of loops X maps to, well, these rationally, hom of the homotopy. Oh, and I should have maybe said -1 there, sorry, homotopy of X into Q, and that must be surjective. And so yes, you can use Chen integrals, but one point I'll make next time is that you get a very different geometry you're looking at. So, I'll discuss this next time. But sorry, it's hard to address all the threads that one would like. All right, let me stop sharing again and see if there's any other message. Great. Why don't I stop the stream and